Download this code from codegive.com, link in the description below. OK, let's dive into the concept of domicile and how it can be tackled using code, particularly in a problem-solving context relevant to J/K students or those new to programming. I'll aim to make this comprehensive and easy to understand, covering the theoretical background, potential coding approaches, and illustrative examples. What is domicile? In context. In a simplified programming context, domicile, or home location, refers to a fixed, designated point, usually coordinates, in a two-dimensional, or multi-dimensional, space. The core problem generally involves calculating the distance between other points and this fixed domicile point. Sometimes, you might need to find the closest point to the domicile from a given set of locations. This type of problem appears in various forms, such as finding the nearest facility. Imagine a map with warehouses. The domicile is the city center, and you need to find the warehouse closest to the city center. Network optimization. In a computer network, a server, domicile, needs to communicate with several clients. You need to find the client nearest to the server to optimize initial connection. Game development. An enemy needs to reach a player's base, domicile, quickly. 2. Core concepts, distance calculation. The fundamental calculation at the heart of domicile problems is finding the distance between 2 points. The most common method is using the Euclidean distance, straight line distance. Euclidean distance formula *. If you have 2 points, A, x1, y1, and B, x2, y2, the Euclidean distance between them is distance equals sqrt, x2, x1, caret 2 plus, y2, y1, caret 2. x1, y1, coordinates of point A. x2, y2, coordinates of point B. sqrt, the square root function. Caret 2, raising to the power of 2, squaring. 3. Coding the distance function. Let's create a simple Python function to calculate the Euclidean distance. Explanation. 1. Import math. We need the math module to use the math.sqrt function, which calculates the square root. 2. Def Euclidean _distance, x1, y1, x2, y2 *. This defines a function named Euclidean _distance that takes the coordinates of 2 points as input. 3. Distance equals math.sqrt, x2, x1, 2 plus, y2, y1, 2, *. This line calculates the Euclidean distance using the formula we discussed earlier. 2 is the exponentiation operator, raises a number to the power of 2. 4. Return distance *. The function returns the calculated distance. 5. Example usage *. The code demonstrates how to call the function with sample coordinates and print the result. 4. Domicile problem example and solution. Let's create a complete example where we have a domicile point and a list of other points. The goal is to find the point closest to the domicile. Explanation *. 1. Find _closest _point, domicile _x, domicile _y, points, *. This function takes the domicile coordinates and a list of points as input. The points list contains tuples, where each tuple represents a point, x, y. 2. If not points, return none *. This handles the edge case where the points list is empty. Returning none is a good way to indicate that there's no closest point if no points are given. 3. Closest _point equals none *. We initialize closest _point to none because, initially, we don't know which point is the closest. 4. Min _distance equals float, INF, asterisk we initialize min underscore distance to infinity, float, INF. This ensures that the first calculated distance will always be smaller than the initial min underscore distance. It's like setting the initial best score to a very high value. 5 for point underscore x, point underscore y in points asterisk we iterate through each point in the points list. We unpack the tuple into point underscore x and point underscore y for easy access. 6 distance equals Euclidean underscore distance, domicile underscore x, domicile underscore y, point underscore x, point underscore y, asterisk we calculate the distance between the current point and the domicile using our Euclidean underscore distance function. 7 if distance min underscore distance asterisk this is the core logic. If the calculated distance is less than the current min underscore distance, it means we've found a point that's closer to the domicile than any point we've seen so far. 8 min underscore distance equals distance asterisk we update min underscore distance to the new, smaller distance. 9 closest underscore point equals, point underscore x, point underscore y, asterisk we update closest underscore point to the coordinates of the current point. 10 return closest underscore point asterisk after iterating through all the points, the function returns the closest underscore point, which will be the point with the smallest distance to the domicile. 11 example usage asterisk the code defines a domicile and a list of points, then calls find underscore closest underscore point and prints the result. V. Other distance metrics, beyond Euclidean. While Euclidean distance is the most common, other distance metrics can be relevant in specific situations. Asterisk Manhattan distance, taxicab distance. The distance is the sum of the absolute differences of the coordinates. Distance equals x2, x1 plus y2, y1. Asterisk useful when movement is restricted to horizontal and vertical paths, like a taxi in a city grid. Asterisk Chebyshev distance, maximum distance. The distance is the maximum of the absolute differences of the coordinates. Distance equals max, x2, x1, y2, y1. Asterisk useful in situations where movement is allowed in any direction, but the cost is determined by the largest difference in any single coordinate. 6. Advanced considerations and extensions. Asterisk higher dimensions asterisk the same concepts apply to 3D or higher dimensional spaces. The distance formulas are simply extended. For example, in 3D Euclidean distance, distance equals sqrt, x2, x1, caret 2 plus, y2, y1, caret 2 plus, z2, z1, caret 2. Asterisk optimization asterisk for very large data sets, brute force calculation of distances can be slow. Techniques like KD trees and ball trees are used to efficiently find nearest neighbors. These are beyond the scope of a beginner's tutorial but are important to be aware of. Asterisk weighted distances asterisk sometimes, you might want to give different weights to different dimensions. For example, the difference in the x-coordinate might be more important than the difference in the y-coordinate. Asterisk using libraries asterisk libraries like NumPy and SciPy offer highly optimized distance calculation functions. 7. Practice problems. Here are some practice problems you can try. 1. Nearest store asterisk given a domicile address, latitude, longitude, and a list of store locations, latitude, longitude, find the closest store to the domicile. You'll need to convert latitude/longitude to x/y coordinates if you're using a flat plane approximation, or use more advanced geospatial libraries for accurate calculations. 2. Delivery zone asterisk a pizza shop has a domicile and a maximum delivery distance. Given a list of customer addresses, x, y, determine which customers are within the delivery zone. 3 closest cell tower asterisk given a domicile location and a list of cell tower locations, find the closest cell tower. Calculate the signal strength at the domicile based on the distance to the closest tower. You'll need to define a signal strength function that decreases with distance. 8. Key takeaways. Asterisk domicile asterisk a fixed point, usually coordinates, in space. Asterisk distance calculation asterisk the core operation. Euclidean distance is most common. Asterisk code asterisk write a function to calculate the distance between 2 points. Asterisk problem solving asterisk iterate through a list of points, calculate the distance to the domicile for each point, and keep track of the closest point. Asterisk flexibility asterisk adapt the distance metric and logic to suit the specific problem requirements. This comprehensive tutorial provides a solid foundation for understanding and solving domicile-related problems. Remember to practice writing code, experiment with different distance metrics, and consider how you can optimize your solutions for larger data sets. Good luck.